Okay, so I want to begin this next topic by discussing one of the things I was trying to say offhand yesterday during our lesson. And who asked it again? Was it Noah? No. Yeah, the wind thing. That was you. Okay. Talked about the wind outside, and that was a great question because that actually leads to the start of our next topic here about systems. I need you guys to know about the three types of systems. Okay. The first one is an open system. Let's use our classroom as an analogy. An open system means that anything can come and go, specifically matter or energy. And so the analogy of our classroom right now is the door is open. Could Kevin walk in with the morning announcements? Yeah, no problem, right? Could anybody leave right now and go to the bathroom? Absolutely, right? Alex left right now, right? That's an open system. If you have a stopper on a test tube, if you lift the stopper off, could stuff get inside? Yeah. Now, here's why we had an open system yesterday. When Brady dropped the volleyball or the basketball, was it possible that like something could get in the way of it? Yeah, I'm not sure that it did, but like I gave a silly example of like, could a bird have like flown underneath the ball and run into it? Okay, that means it's an open system. Okay. Second system is a closed system. You put a lid on it. Okay. If I were to all of a sudden go close that door, well, now people cannot go in and out, right, without opening it again. The example I was trying to give yesterday, I'll see whether I can draw it better, would be imagine that again, here's the roof, here's Brady standing on the roof with the ball. If I were to have like a long tube and he dropped the ball inside the tube, well now that would be a closed system because now if some sort of, I can't even draw a bird here, this is a bird. If a bird tries to like fly and hit the ball, it couldn't because it would run into the big plastic tube surrounding it. Right? That's a closed system. Okay. Ideally, we would love to have what's called an isolated system. And an isolated system not only prevents matter from leaving, but this also prevents energy from being lost. Energy is not lost. Okay. And the best way to make an isolated system is in something called a vacuum. And if you haven't heard of the concept of a vacuum before, basically you suck all the air out. And if you suck all the air out, there's now no longer any wind resistance or air resistance. And now not even friction would slow something down. Okay. You guys remember our Hot Wheels lab, right? Why did the Hot Wheel car eventually stop? Well, it was due to friction, right? Friction meant that like energy was being lost slowly over time. Every time that the car's wheels turned, they lost a little bit of energy, probably to heat. And every time the car bumped the sides of the wall, it slowed down a little bit because it lost some energy, right? Ideally, in an isolated system, no energy is lost whatsoever. The best example I've got right here is imagine you have a thermos. If the thermos is closed, then it's a closed system. But if the thermos can prevent heat loss, now it's isolated as well. Okay. That's what we'd like to assume. We'd like to hope that there's not energy loss due to wind resistance or friction or whatever it happens to be. So we assume they are, but they're probably not. So here's what we want to be able to start doing with some of our calculations. This is called the law of conservation of energy. And the idea is that mechanical energy, the word we use is it's called conserved. What that means is whatever you start with for energy, ideally you should finish with the exact same amount of energy. If I give you 100 joules of energy to begin with, I want you to have 100 joules when you're done. That's basically what the conservation of energy law states. The problem is that's not actually how things work. Okay? Ideally, this would be true in a truly isolated system. But chances are due to friction or loss of energy due to maybe sound or heat, maybe when you're done you only finish with like say 98 joules of energy. That's usually what happens. But we're going to assume that it's perfect. There's no loss. Okay. I want to go back to this picture I had right here of Brady dropping something off the roof. What sort of energy did the ball have at the top of the roof? Potential, yeah, because he hadn't actually dropped it yet. Specifically, he had gravitational potential energy. Mass times gravity times height was what the energy was, right? And as the ball falls and hits the floor, that energy should get converted into kinetic because it's now moving. Ideally, all of this energy should have been converted from potential to kinetic, ideally. But let me show you a scenario where that wouldn't happen. I'm going to drop a couple of items. I'll do it from the front of the room here. Here's 2 pens, right? If I drop them, they should hit at the same time, right? But let me give you a different example. Here's 2 more objects. Why did one take so much longer? Well, it's not about the density or the weight, because like even let's take these 2 objects. Let's take something heavier even. These are not the same weight, right? Will this one that's heavier fall faster? No, it doesn't. I don't want to, well, maybe it will break, but let's try it. No, they still hit the same time. Okay. Galileo even did an experiment, right? Remember the story from yesterday, how Galileo dropped a couple cannonballs and they still landed at the same time? The reason why this guy right here falls at a different rate is that there's all that air resistance. It's losing energy due to like friction. Literally, there are air molecules right underneath here, and they're kind of floating underneath. It's the same principle as to why airplanes float, is that it's literally riding on top of the air. See? Doesn't matter what they are, but this thing right here, due to its like really flat surface there, is not as aerodynamic. Imagine you had a race car, right? Race cars have a few different features on them that they use to try to make them more aerodynamic, right? They make them very slim and low to the ground. They may have like a spoiler on the back to try to like keep the airflow as tight as possible, right? Because what they really want to do is prevent friction, okay? What I'm saying right here is that when we drop this object from the top down to the bottom here, we're assuming that there wasn't a lot of friction due to like air resistance. And it probably wasn't, right? As it being a ball that fell, it probably more or less, you know, sliced right through the air, right? But here, I need my writing board again. Where did I leave it? Right? This kind of explains why when we want projectiles to go into the air, just take a basic, like say a bullet. A bullet doesn't look like this. On the end of the bullet, you put a bit of a tip, because what it does is it causes the air resistance to kind of like slice off to the side. Does that make sense? Like even a rocket ship does the same thing. If this is a rocket ship that's about to take off for the moon, and it's about to thrust, right? It's always kind of pointed on the end, because that way the air resistance can kind of like slice off to the side. Does that make sense to you guys? Okay, so anyways, I'm getting a little off topic, but that's what I want to try to discuss here, is the idea right here that whatever energy you begin with, ideally we should finish with the same amount, but sometimes you lose a little bit due to like air resistance and stuff. Okay. So the term I want to use then is mechanical energy. Mechanical energy is defined as the sum of all your energies. Basically, take your potential and your kinetic and add them up. And whatever you start with, you should finish with. Okay. So let me give you a couple of pictures before we do some math. Let's say that this bike rider is riding up the hill. Right here at the bottom of the hill, he has kinetic energy because he's pedaling, right? Then at the top of the hill, well, now at the top of the hill, he now has potential energy, right? And then as he falls back down to the bottom again, he's got kinetic again. Ideally, what should happen in a perfect world, let me give you an example of a pendulum. You guys know what a pendulum is? Like you hang like an object on a rope like this. If I pull it all the way out to here, it should swing all the way here, and all the way back, and all the way here, and all the way back. But every time it does this, it goes a little bit less. Why is it going a little bit less? Due to friction, air resistance. Yeah, right? But ideally, it would go all the way there, all the way back, and keep doing that for forever. In our lab yesterday, remember, we even made a graph that looked like this. The ball went all the way down, hit the ground, and when the ball bounced back up, but it only made it about this high. You guys remember doing that graph a little bit there? Ball started way up here, bounced and hit the ground, and came back up again. At the very, very top, the ball had gravitational potential energy. Then as it fell and it hit the ground, it had like kinetic energy. But then it turned it back into gravitational energy. But why is there like some lost energy? Well, at this moment right here, there was energy lost. For example, here's one form of energy that it was lost to. Sound. You know, when the ball hit the ground, we could hear it, couldn't we? Well, that energy didn't come from nowhere, and so the ball lost some energy to sound. And I bet you there's also some energy lost due to heat as well, because as the ball hit the ground, it probably compressed. You know, the ball used to be like this, and if we had a slow motion video, you might have actually seen it squish down a little bit. It probably lost some energy due to heat as well. And that's why the ball didn't quite make it as tall as where it started as. Okay. Ideally, though, in an isolated system, it would. Okay. I've got some more pictures here that hopefully I can kind of explain what's going on here. Basically, there's a series of them. Imagine that there's a car that's about to go through this loop-de-loop, the next loop-de-loop, and then up and down. Okay. The way these bar graphs work, if you can kind of see this, the first one here stands for your kinetic energy. The second stands for your potential, and that's potential. And the third graph the TME stands for your total mechanical energy. Okay. And basically the green bar is all the energy that you have. Okay. It's either energy of motion or it's because you're still above the ground. Look at the first picture right here. This, I don't know, let's assume it's like a race car, I guess. This race car right here is not moving. So can you guys see how it only has potential energy? Then the race car goes all the way down the track, and now it's down here at the bottom. Does it have potential energy anymore? No, because it's now as low as it can get. What ended up happening, though, is all of this blue bar of potential has now turned into kinetic, because now it's moving. Now let's say it goes to the loop-de-loop, and it's back up here. Well, now it has some of each. If I were to take this and add them together, though, it would equal the total amount, ideally. Okay. Then it goes through this loop-de-loop. Well, it's got more kinetic energy because its potential is lower because it's not quite as high. You know, here, can you guys again see how these two numbers right here, they would equal that one there? And then finally, maybe at the end here, it's just got kinetic because slowly over time, there's no potential left. That is what ideally in an isolated system would happen. But, no. You're not the only one who missed the bus this morning. It's okay. I'm glad you made it, buddy. Yeah, ideally what happens is that this bar right here for total mechanical energy stays the same the whole time, but in a real world scenario, it slowly but surely diminishes, just like our Hot Wheels track. Slowly but surely, the car eventually slowed down. Okay. Yeah, so that's what I've got right here. Sometimes we want to consider thermal energy, which is friction, because you're going to lose that energy due to friction. Okay, let's try some math questions now. Now that I hopefully have kind of described the concept to you, what we're going to do today is we need to basically take the potential energy that you have and turn it into kinetic, or vice versa. Let's draw a picture. You have a heavy object, is dropped from 12 meters above the ground. This is basically the exact same as our lab yesterday. Here is Brady standing on the roof, dropping an object, and the object is going to fall that far. What sort of energy does it have at the very, very top of its flight? Just potential, yeah. So energy due to gravity is mg delta h. And as it hits the ground, well, the instant it hits the ground, it just has kinetic. So we just need to basically calculate this energy right here, and then there's kind of a link here. All of your gravitational energy will turn into kinetic. So let me give this a try. This is literally what we did in our lab yesterday. Mass, 50 kilograms. Times gravity, 9.81. Times height, 12. Need my calculator. Okay, so I did 50 times 9.81 times 12, and I got this value here, 5886. So if you have your calculators, just make sure that you got the same thing as me. That's how much energy the ball had when we began in joules. Ideally, all of this gravitational energy will now be converted into kinetic energy. So ideally, this number is now this number, if it is an isolated system. It probably isn't. So you probably lost a little bit of energy due to like wind resistance and friction and stuff like that. So it probably wasn't 5886, it was probably like 5881. We probably would have lost like a few joules of energy due to air resistance, but we're going to assume that we didn't really lose any energy at all. So then I go use this formula down here. And so I'm going to make this one go up if I can. Our kinetic energy is now 5886 1/2. Our mass is still 50, and we need to solve for v squared. So can you guys kind of see the link there? I did this times this to get my energy of gravity, but ideally all of my gravitational energy should become kinetic, so I just put that number right here. 1/2 mv squared. Now we just need to use algebra to rearrange. So how do you undo a 1/2? You times both sides by 2. How do you undo the times by 50? Divide by 50. And how do you undo a square sign? Square root. So, I mean, it's not the prettiest anymore, but what we really need to do to get velocity is do 5886 times by 2, divide by 50, and square root the whole thing. And now we have our velocity. I got this number here, 15.344, etc. I'm going to pause here for a second. I just want to make sure everybody who's trying it has time to catch up. Anybody else calculate that number as well? You got that number? Okay, one more thought though. We need to round though. This is why sig digs are so important, because 15.344, etc. implies, if I don't round it, that like I know exactly this digit and this digit and this digit precisely. And I don't think we do on this one here, because we're going to need to round. Just like how Brady said it was about 6.5 meters above the ground, I have to use the limiting number of significant digits. So this had 3 digits, and this had 3 digits, and I guess 9.81 had 3 digits. Even though I didn't write them here, they all had 3 digits, so this better get rounded to 15.3. That is as certain as I can be. That's how fast it's going to hit the ground then. It might be 15.344, but like I can't be certain of it. Does that make sense? So one more time, I'll talk through the process. I found my gravitational energy by doing mass times gravity times height to get that gravitational energy. We're assuming no loss of energy. So as the gravitational energy turned into kinetic energy, that same number went down here. It was equal to 1/2 mv squared, and then the scribbles that you see here is the algebra of undoing the equation. So I times by 2 to get rid of this guy here. I divided by 50 to get rid of this one here, and in yellow I square rooted. Okay. Once you get the hang of this, you know how I was talking earlier about the whole unconscious, being good at things or not? Eventually I want to get you guys to the point where you don't even need to think about it, and it's just kind of on autopilot. It's like, okay, just times both sides by 2. The best way to get to that point, practice. So you need some practice to get to that point though. Okay, let's try another example. A kid is playing with his toy at the top of the balcony. The balcony is 19.2 meters above the ground. He drops the toy. How fast will it hit the ground? Why don't I give you guys a few minutes and try this question? Because it's literally the exact same process as the last one. There's literally someone dropping something. Try to see that you guys can figure out how to solve this one without me doing it. So can I give you guys like 2 or 3 minutes to try it yourself? have it upstairs though. So as soon as I'm done doing this, I'll grab the key and lock it. I finally brought it upstairs at least. Yeah, totally. I get it. Give it a try, guys. If you're not actually like right now, if you're just playing on your phone or you're just chatting, you're kind of missing the point, right? I want you guys to try it by yourself and see whether you can do this yet. If you can't, then I can try to help. Okay? But don't just sit there and do nothing. If you're stuck, let me know. You're looking to do something like this. First, you want to find the gravitational energy of mg delta H. Start with that. If you're stuck. Yeah. Sure.
So for this one,
Yeah.
We convert grams to kilograms.
Absolutely.
And when we look at significant digits, do we look at this number or at this
And that
number?
makes this one an issue because this guy right here, I'm really uncertain as to how many significant digits it has, aren't I, right? Like, this guy could have two or three digits because it really wasn't written in a right way there. So since this one had 3 and this one had like 2 or 3, it's probably best just to go with it as 2 as the most that we're certain of, because I'm really not sure how many digits this one really was rounded to. Does that make sense?
Solving a problem like that,
Yeah.
For significant digits, we are using the number that's given us in the problem.
Exactly, yeah, because that's what like somebody measured, right? Just like Brady measured 6.5 meters for us, and this one we measured on the scale there. Does that make sense? So whatever was given here. So since this one has 3 and this one has 2 or 3, when we're done, we should probably give it 2. Yeah, as the best way that we are certain of. If you give it more digits than that, you might be overstating things.
What's the gravitational energy of potential energy?
Yes. Yeah. So yeah. For us right now, yes. But we talked yesterday or a previous day about how potential energy, there's also energy in like elastics and in nuclear bombs. But like the only formula we use for potential energy right now is gravitational. Yeah. Okay, so why don't I help walk you through this a little bit? Hopefully you got something, maybe not all of it, maybe you started. I do want to point one thing out here. This mass right here was 120 grams. That often needs to get converted into kilograms. So hopefully you did something like this. 0.12, because that's what happens when you divide this by 1,000 and make it into kilograms. Okay. Times by gravity, 9.81, times by your height of 19.2. So 0.12 times by 9.81 times by 19.2, I have an energy value of 22.60224 joules. Now, we're not done the question yet, so it's really not good to round this number yet, because we're really not finished anything yet. So I want to keep this value still for now, and later I will round though. So now I want to make it equal to kinetic energy. The kinetic energy formula is 1/2 mv squared. So assuming no loss of energy, which probably isn't actually true at all, but assuming, that same mass goes here again, nv squared. You're hopefully this is getting closer to autopilot. Times by 2 on both sides, divide by 0.12 on both sides, and square root. Now you got your velocity isolated. So times by 2, divide by 0.12, and square root. Here's what my calculator gave me. So check yours against mine. I got 19.40, etc. Okay, now we got to talk about units and significant digits. This right here was measured with 3 significant digits. Perfect. But what about this one right here, 120 grams? It could be 3, it could be 2. That's that ambiguous number. We hate it when someone writes it like that because, like, well, what was it rounded to? Was it rounded to the nearest ones or to the nearest tens? And so because this was written with 2 or 3 significant digits, we should go with the lower of the 2 numbers because we don't want to be more exact than fair. So let's go with 2 sig digs. Let's call this 19 meters per second. To call it 19.4 might be a little bit too much information that I actually know. Okay, let's not overstate it. I mean, maybe this is another silly example, but if I were to try to guess your age, it wouldn't be incorrect for me to say that you're a teenager. But that's not really narrowed it down, right? And maybe I'm pretty sure you're 16. But, like, I might be guessing if I said that you were 16 years and 4 months. Because what if I wasn't really sure that you was 16 and 4 months? You know what I mean? So sometimes it's better to be a little less specific so that you're actually for sure correct. Does that make sense? Yeah. This one right here, because we're not really done with it yet. Does that make sense? Right? Like, we really don't want to round until we're finished the entire question. Let me give you a different example here. Let's say that you took 0.12 and you times by 9.81, and then you found an answer, and then you times by 19.2, but every single step along the way you rounded. Wouldn't that, like, slowly but surely cause your answer to be, like, incorrect? Does that make sense? So don't round until we absolutely have to finish the question. Good question. Yeah. Can I show you guys a trick if you have the right calculator, actually? Here, this is a graphing calculator I can pull up on my screen here. I know not all of you have this particular calculator, but enough do that this is useful. Hypothetically, let's say that you do get an answer that's like one of those like crazy long decimal numbers. This is a cool trick I can show you. I'm just going to do like, say, 45 times by 9.81 times by 8. Let's just, hypothetically, that's this number right here. No, that's not you good. Let's divide it by 7. There we go. You got this like stupid crazy number here, right? And like you know that you don't want to round it yet because you need to use it later. Here's a cool trick. Press STO. It's right above the on button, STO, if you have this calculator. Okay. And what it's going to do now is it's going to store your answer as any letter you want it to be. And you might notice that there's letters hidden. Like mine is in green. Yours might be in blue or in yellow or something like that. So to get to that, you press like, say, alpha. And I'm just going to pick like this one. I'm going to make it be alpha A. If you press the store button and then make it alpha A, and I press enter, then from now on, every time that I go alpha A, that answer shows up. So then, if I have to, like, say, take alpha A, that number right here, I can take the entire number, times it by 2, divide it by 50, and then, like, square root my previous answer. Oh, that's not a square root. Square root my previous answer. Then I never have to, like, lose any decimals along the way. So one more time in case you didn't catch that. If you want to, like, save a certain number, it's right above the on button, STO for store, and then just literally store it as, like, any letter. And now you have that number saved. If you have a calculator like that one there, they're all different. Most of them have a store function. Yeah, so we'll have to look at yours a little bit later if that's okay. But we'll be able to store it as something. Yeah. We just got to figure out how. I'll look at yours later. You know how? Okay, we'll look at yours in a bit. Okay. Well, let's try another example here. This one's a little bit different. I want you to look at the numbers I gave you. A heavy object with a mass of 20.6 kilograms is thrown vertically down from the top of a building with a velocity of 10 meters per second. What's different this time? Yeah, we didn't just drop it. If I'm doing my image right here, at the top right here, when Brady has the ball, Brady just dropped this ball so that all it had was potential energy. But now there's potential and there's kinetic energy because he's actually throwing it downwards. So here's what's going to happen. We're going to have to look for potential and kinetic to start with. And then both of these will equal the kinetic when we're done. Just a slight little twist. So it's going to look something like this. We're going to need to do the mass times gravity times the height. 1.00 times 10 to the 2 is actually the number 100. But this implies that it's like been rounded to the nearest ones. So that will be my potential energy. But I need to add to it the fact that it actually was thrown. So there's extra energy because this person threw it down. What was the speed? 10. So now I need to figure out how much gravitational energy it had and how much kinetic energy it had, and add them together. So I didn't do 20.6 times 9.81 times 100. And so I'm going to write this down in red, just one at a time. Due to just gravity alone, there's 202.08.6 joules just for that part there. And 1/2 of 20.6 times 10 squared means we get to add on an extra 1030 joules due to kinetic energy. There's more energy because it's being thrown downwards now. So add these two numbers together, and the total amount of energy is, I got a grand total here of 21238.6. So hopefully I didn't lose you here. Let me try that one more time. I did mass times gravity times height to get this 20,000 joules of energy just due to it being above the ground. But because it was also being thrown, now we have to add on the kinetic energy of the person throwing the thing, which is 1/2 of mv squared. I added these two numbers together to get a grand total energy of this. If I asked you to classify this number right here, we would call this the total mechanical energy. I'll say that one more time. This number right here, which is both of these two numbers added together, we would call this number the total mechanical energy. That's the word we use to describe. Remember these pictures right here, where like right here at the spot right here, this guy is moving, but he is above the ground, and there's like some of both. The total mechanical energy is where you add them together. Okay. So then all I have to do for the last step is make this equal to 1/2 of mv squared, because at the bottom all he's doing is moving. Let's make the mass though be, what was the mass again, 20.6? That's a 20.6 hiding in there. So we've been doing this for a while now, times both sides by 2, divide both sides by 20.6, square root it. Hopefully, this is becoming more like autopilot, okay? Hopefully, if it's not where like you can do it without thinking about it, at least you can do it, but while you're thinking about it, okay? Eventually, I'd like it if you could just like, okay, times both sides. Like it's boring almost at a certain point. It's mundane and tedious, you know. So times by 2, divide by 20.6, and square root that answer. Here's what I got for velocity. Rounded to 3 sig digs, because this gives you 3, that gives you 3, that gives you 3. I got this value. It's 45.4 meters per second. Why is it going so much faster? Because the last example was only going 19 meters per second. Why is it going so much faster? Because he threw it. And, by the way, it also fell from 100 meters, not 6 meters, right? So really 2 things, right? He threw it, and it was really high in the air, guys. it will accelerate at the same rate, but it's starting at a higher initial speed, right? So rather than having to go from 0 to 50, it's starting at 20 to 50, so it doesn't take quite as long to get to that top speed. But it's still going to accelerate at the same rate, 9.81. Okay, this is our last example now. I want to point something out. When you're doing an example, sometimes you can actually maybe like speed things up a little, okay? And if you want to do the initial procedure I kind of showed you, that's fine. But sometimes it's nice to use this formula here that I wrote way back here. It's not really a formula that necessarily can go on your data sheet, but if you want to write this down, feel free. Potential energy plus kinetic energy should equal potential plus kinetic. We could almost like write out this as our starting formula, if that makes sense. So I want to try this like a different method. I'm going to write that formula out. Your potential energy and your kinetic energy that you begin with should in theory equal your potential energy and your kinetic energy that you end with. Let's try this example. A child shoots a Nerf gun from the top floor of the house at his sister. The gun can shoot the foam projectile 3.6 meters per second, and when the foam dart hits the sister, it's now going 8.2. How is the dart shot from? I'm going to start trying this like in a different way of phrasing it. It's still going to work out the same way for math, but here's a different way of organizing it. When the brother is shooting the dart, it has potential energy because there's mass times gravity times a change in height. And he began with kinetic energy because he literally shot the dart, so there's a 1/2 mv squared. But this is when he shoots the dart, and this is when it hits the sister. When it hits the sister, does it have any potential energy left, though? I'm assuming she's on the ground, more or less, right? So really, there's no potential energy left because the dart's no longer above the ground, right? The brother in the picture, the brother is up here with the Nerf gun. Sister's down here on the floor, right? And the dart eventually hits them. That does actually look a little gruesome, doesn't it? Sorry. I'm not the best drawer. Right? But would you guys agree that up here there is potential energy because he's above the ground, and there's kinetic energy because he shoots the dart, and down here there's only kinetic energy. So I'm going to make this whole thing be a 0. We'll get rid of that picture, I guess. All right. Here's what I'm trying to get at, is that perhaps you may like to write it in this orientation and do it all in one big equation. Rather than doing little equations by like one at a time, you might like doing it like this. Okay. Now I'm going to start plugging in some numbers where I know them. Do I know the mass? 12 grams. But I want kilograms. So I'm going to take this number and divide by 1,000 and make it equal to 0.012. So all of my mass numbers here, here, and here are now mass. All right, so I plugged in all my mass numbers. I'll try to color code to help make this clear. Red. Do I know gravity? Yeah, it's always 9.81, so I'll make that one red. Yellow. Do I know how high he was above the ground? No, that's actually the one I'm not sure of, so I guess I got to leave that one as an unknown variable. Okay, this velocity right here in green I'm going to go with is the velocity with which he shoots the dart. So that one was 3.6 squared. And do I have another color left? I guess I got to use the same color again. This velocity right here is the velocity at which it hits the sister, which was 8.2 squared. So if you want to, if this is another way of kind of representing this in your mind, if you want to do it like in all one big equation, you could write it something like this. 0.012 times by 9.81 times by delta H plus 1/2 of 0.012 times by 3.6 squared should equal 1/2 of 0.012 times by 8.2 squared. If you like to, you could write it like all in one big equation. And I guess this, oh, I didn't want to draw that line there. I wanted to move this out of the way. It just depends on whether this like makes more sense to you or not. Because like this right here is considered a term. This is considered a term, and this is considered a term. So what you can do is you can kind of simplify all of these into numbers now, which honestly is exactly what we were doing anyways. Okay? So I'm going to do 0.012 times 9.81. 0.012 times by 9.81. This right here is 0. Hey guys, you're a little loud. Thanks. I got 0.11772 delta H. And I want to add to that whatever this number is. So that's 1/2 of 0.012 times by 3.6 squared. This number here is 0.07776. And then over here, the final number is 0.40344. So, like, you don't have to do it this way, by the way. I want to show you another option for how to visualize it. So, I kind of made a big equation for everything. I didn't count the potential energy because, like, it's on the floor now. I wrote out these kind of equations here, and I plugged in all the numbers I could. These two numbers multiplied to give that. These three numbers gave me that. Those three numbers give me that. The only thing left I have to do is subtract 0.0776 from both sides. And when I'm done doing that, then divide it by 0.11772. So I'm almost out of room here. Hopefully you can see this. Then when I do that, I'm going to divide it by 0.11772. So subtract this number over here, divide by that number, and we're good to go. So 0.40344 is going to subtract 0.0776 and is going to divide by 0.11772. Long story short, when I'm done, I got this value, 2.8. And actually, that wasn't a V. That was a delta H. Because isn't delta H what we were solving for here? So what does height get measured in? There we go. Okay, so 2.8 meters is my answer. Okay. Now, if you don't like this method of organizing things, don't use it. That's fine. I wanted to show you another option for how to keep track of things. Okay, I'm going to shut up in hopefully 2 minutes here. This is not on your quiz tomorrow, so don't freak out about this. Okay. Individually, though, using the potential and kinetic energy formulas, that is on your quiz. Okay. So if I give you just the kinetic energy formula, you should be able to use just that. But like putting them together in this scenario here, where energy is hopefully being conserved and not lost, I'm not going to test you on that yet. Okay. Okay, last thought then. You guys have 20 minutes or so here. You guys can scatter if you want. Let me remind you of some tasks to work on. Okay. Number one, the single most important thing I think you should do in preparation for tomorrow, go over your last quiz and find out why you're making mistakes so I can help you get better. Okay. Hypothetically, though, you finished that, you're good on that, you've looked over my answer key online because I'm putting them online for a reason. Other things to work on, your old lab, which should be due already. I gave you a lab to work on yesterday. Did any of you guys check your email? I emailed the 2 videos that I made of the basketball and the volleyball falling. Do you guys check your school emails ever? Okay. If you can, check your school email. I emailed the video of Brady dropping the basketball and volleyball. Okay. I also posted on my website the tutorial video on how to use that tracking software. I will help with that. Okay. If you're struggling on how to use that software for the remaining part of your lab, I'll help. Okay, because it's new to you, I get that. The last thing you can work on is the assignment. There's only one assignment, guys. It's not like there's a lot of assigned work here, but like you should do it for practice. Okay, and that's all I got. Any questions? Yeah. Oh, like a just one-on-one question? Any big picture questions as to what we're up to? Okay. If you guys want to scatter, that's your call. Feel free. Okay. Yeah, let me answer because